Okay, so we are starting on a new topic today. It's a little bit of a catch-all assignment. I would say that the way I look at this course, it's sort of a turning point. Basically, this is the last week that we will be focused on learning C++. And starting with next week, and also going on into your next programming class, the focus will be very little on actual C++ stuff, and it will be almost completely on just techniques for doing things using C++ that you may not have thought of on your own, but using stuff about C++ that you already know. So as far as I can think of, when we study linked lists, which is the only remaining topic that we have, I won't be teaching you anything new at all about C++. We will just be using stuff that we've already learned to implement some more interesting computer programming techniques. So in my mind, anyway, that's sort of a turning point. And so it turns out that this week's topic can turn out to be sort of a hodgepodge, sort of like whatever we haven't covered already and we need to before we dive into the next thing. What you see on the screen now is sort of a list of those things. We're going to be talking about templates, which is a fairly major subject. We're going to be talking about exceptions, which will be a little quicker but important. And we're going to be talking about the standard template library in C++, which is super important, actually. And then we're going to be talking about iterators, which some might argue is actually sort of a subtopic of the standard template library. So these are sort of the four things to focus on as we're talking here. In terms of the order, I'm going to be talking about STL first, and then templates, and then exceptions. Okay, so standard template library. The standard template library is a set of classes available for programmers to use that act as containers for other objects. So that's sort of an important word there, containers, right? That may sound weird at first, but it's actually pretty simple. We've already talked about a couple of containers. We've talked about arrays. Arrays are variables that contain other objects, right? You can have an array of ints, or you can have an array of strings, or you could have an array of feet, inches objects, or whatever. So that's a container. You could also think of something like a struct as being a container, right? A struct contains other variables or objects, right? You could have a struct that contains a feet inches object and a string object, for example. But the containers we're going to be talking about in the standard template library are going to be like that, but way, way more powerful and with a lot more features, right? As an example, one of the standard template library classes is vector. And an STL vector is similar to an array, but easier to work with and with a lot more features. So before we go any further, actually, let me just show you quickly where I like to go to get my information about the standard template library classes. I go to c++.com. and I click on reference. And then I click on containers. And that gives me a list of all of the, at least all of the header files in the standard template library that are containers. Okay, and so some of these may have more than one container inside. For example, the map header file, and I don't expect you to understand what any of these are at this point. At this point, just think of them as a list of containers that you will learn about later. But if we click on the map container, the map header file, you're going to see that there are actually two container classes inside that header file. There's a container class named map and a container class named multi-map. So I'm just putting that out there for no other reason than to just say that some of these header files may have more than one container class inside them. Okay, so you can look at these if you want. We are not going to be talking about any of these, except we're going to talk about the vector container class. And let me just point out, I'm going to just say, okay, look, there's also a class here called forward list. And I'm only saying that just because later on during the lecture, I may refer back to the fact that there is a container class named forward list. But you don't really need to know anything about it at this point. For our purposes, we're just going to focus on a single container class, the vector container class, and that's sort of going to function as our introduction to standard template library. And I suspect that you will be talking a lot more about that in CS 315. Often when courses like CS 315 are taught, so data structures courses, often when they are taught, basically 80 to 90% of it just turns out to be, let's talk about each of these container classes and how they work and how they are implemented. That's, at least 80% of what a data structures class turns out to be. Okay, so we're going to talk more about vector. So a vector is just like an array. You can have a vector of anything, right? So you can have a vector of ints, you could have a vector of feed instance objects, you could have a vector of strings, whatever. The difference is that vectors are a lot more powerful. There are a lot more things you can do with vectors. And just as an example, you can always add something to a vector, and you don't have to worry about resizing the vector if it's already full, right? With an array, even a dynamic array, if you try to add something to an array and there's no room for it, then either you can't do it or you're going to have to somehow resize it, right? We did that a little bit, right? We did that with the myString class. In the myString class, if we wanted to put something into the C string that doesn't fit, we had to create a new myString that was large enough for the C string, and then copy the whatever you wanted to into that new dynamic array. So we've done something sort of similar to this with the myString class. And I guess what I mean to say by that is we've done something similar to how the vector class would be implemented, right? In one sense, none of what I just said really matters if all you're going to be doing is using the vector class. In terms of using the vector class, all you need to know is you can always add something to it, and you don't have to worry about whether you are exceeding the capacity of the vector. Let's see. So the way that you declare a vector is like this. So first of all, to use a vector, you have to # include vector at the top of your file. And that's going to be true for all of the standard template library classes. Anytime you want to use an STL class, you're going to have to # include it at the top. And then to declare a vector, we would say something like vector int v. And so that is, whenever we use vector, there actually is no such type in C++ as just vector by itself. Whenever we use vector, because it's a container class, we also have to specify what type of object the vector is storing. So if we want a vector that is storing ints, we put int in the angle brackets, right? So inside those angle brackets, I could have put string, I could have put my string, I could have put feet inches, whatever, char, double, and so on. So that's how you declare a vector. The main technique for putting something in a vector is the pushback function. That would look something like this. Okay, and what that means is just add something to the end of the vector. Okay, and you can do this forever, right? I could have I could declare a vector, and then I could have a for loop going 10,000 times that just keeps putting something onto the back of the vector, and I don't have to worry about whether the vector is big enough. If the vector's capacity is reached, C++ will just automatically create a new, resize the vector so that it's big enough to store whatever I am putting there. Also, on the other hand, though, the programmer can manually control the size or the capacity of the vector, right? So for example, when I declare the vector, I can tell C++ what I want the capacity of the vector to be. Now, even with this, this means that the vector v is going to have a capacity of 100. But if I push back 200 numbers, that's still going to be okay. When I go to push back the 101st item, the vector is just going to automatically get resized to a bigger size so that it can contain the 101 items. Okay. There's another way to manually control the capacity of a vector. I could say v.resize and make it, 1,000, for example. Oops. Okay, and all of this that we're talking about has to do with the capacity of the vector. Okay, so I'm going to get a little more detailed about how this automatic resizing of the vector happens. When you try to call the pushback function and the vector's capacity has been reached, what's going to happen is the system is going to create a new vector that is larger. And it turns out that the C++ standard doesn't say exactly how much larger to make it, so that depends on the system. One common and very simple system is that if the vector's not big enough to store another item, you just double the size of the vector, right? So if the size of the vector was 8 and you call v.pushback, there's already 8 items in the vector is going to get resized. Now it's going to be a size 16 because the size is going to, excuse me. Because the size is going to be double, okay? It's not always going to be exactly double. In fact, in Visual Studio, I think that there's some sort of an interesting formula where the size of the vector is increased, but it's not quite doubled. But you can, that's a good sort of simple and commonly used technique. Okay, so basically what we're going to do now is I'm just going to show you a client program that uses vectors and point out a couple of the additional member functions that are going to be used. Okay, so here's some code. You can see in this code where I have declared a vector of integers. And then I'm going to have a for loop going from 0 through 19. And I'm going to put all of those numbers 0 through 19 into the vector. But each time I put something into the vector, I'm going to print out what the current size is and what the current capacity is. Okay, so just to be clear, the difference between size and capacity. Size is the number of items that we have actually inserted into the vector. Capacity is how many items the vector can currently hold. Okay, that capacity can change, but there's still a concept of capacity. What that corresponds to is sort of behind the scenes. The way a vector is implemented is with a dynamic array. And so a dynamic array always has a size, right? And then the way that the vector works is if I try to add an item to the vector, and if it has already reached its capacity, then behind the scenes, inside the pushback function, I'm going to have to create a new dynamic array to store the vector that's going to be bigger than what it was before. And then I'm going to have to copy the contents of the old dynamic array into the new dynamic array, and then deallocate the old dynamic array. Pretty similar to what we did in the MyString class when we had a MyString that was bigger than what the current dynamic array was allocated for. Okay, so anyway, I mean, I guess that the last few sentences about how the vector is implemented, you probably don't need to understand at this point. I'm just sort of giving you a sneak peek behind the scenes in case that helps things make more sense. But if it didn't make any sense, that's okay. So I'm filling up this vector, and then I'm going to call the print function, which prints the vector out, and it actually is going to print it out twice. The first time it prints it out, I'm going to be calling a member function of the vector class named @. And the second time I print it out, I'm going to be just using square brackets the same way I would if it was an array, right? So what this tells you is the square brackets operator is overloaded so that it works with vectors. The only difference between using @ and using the square brackets with a vector is that with a vector, the @ function is actually going to do range checking to make sure that that I is a valid index, right? It doesn't go, it isn't larger than the size of the vector. If it is larger than the size of the vector, it's going to do something that we're going to talk about soon. So this may not make sense at this point, but just to put it out there, it's going to throw an exception telling you that I is out of bounds. If you use the square brackets to print or to access the vector, it's going to behave just the way it would if it was an array, right? It's just going to try to access that element. And then it's just going to see what happens if it can't. It's not going to check anything. Okay, so let me run this, and then I will ask if there are any questions about anything that's going on in this program. This is all pretty familiar stuff, right? Not that much stuff is new. I'm just introducing this fact that we can declare things to be of type vector. We can use the pushback function, and then we can print things using @ or square brackets. All right, so let's take this first spin. So I'm going to say, all right, so we have some interesting things to look at here. First of all, I printed out the capacity before I ever put anything into the vector, right? So I just declared a vector and then printed the capacity, and it came out 0. So what that tells me is that if I declare a vector and I don't tell it how big to make the vector, the default is it's going to be of size, the capacity is going to be 0. Okay, just a little trivia there. Doesn't really, probably not all that important. But then if you look here, we're going to be pushing 20 integers onto this vector. And this gives a pretty good idea of what happens when I try to push back something into the vector if the capacity has already been reached, right? So for example, here, the size is 2. That means there's already 2 items in the vector. The capacity of the vector is 2. I go to push another item onto the back of the vector. So the size, of course, becomes 3. The capacity of the vector is doubled to 4. Okay, and then just to look at that, a little later on, here I have 16 items in the vector, and the capacity of the vector is 16. So if I go to push one more item onto the back of the vector, the size, of course, is going to be 17. The capacity of the vector is going to double to 32. Okay? Any questions about what's going on here? Okay. The next thing I want to talk about is something called size type. Okay, and size type is one of those things that's super, super simple to use, but not always super obvious to students why you would ever want to do this. So the students that have trouble with this are usually the ones that, I don't know, like have trouble using something if they aren't quite sure why they're doing it. Anyway, let me just talk about it. So every standard template library, not every, but for our purposes anyway, pretty much all standard template library classes include a type named size type. And the idea is that anytime a client program declares a variable that is used to count items in an STL container class, it should be declared to be of type size type instead of type int. So for example, let me pull up an example of that. here we have the same exact program that I just showed you, but what I've done is the size variable, instead of being of type int, it's of type size type. And because size type is a type that is defined inside the vector class, I have to use the scope resolution operator, right? If I just said size type by itself, I'd get a compiler error because the compiler wouldn't know what that is, because the size type is declared inside the vector class. Okay, so I'm going to talk a little bit about the rationale for having things this way, but the bottom line for you is just to know that anytime you declare a variable in your program that is using an STL class, don't use int. Instead, use this variable size type. I've used it here. I've also used it down here in these for loops, because in both of these for loops, I is a variable that is going up to print me.size, so it counts as a variable that is counting the number of items in a vector. Okay, so that's the bottom line. Now let me just say a couple of things about what the rationale for that is. Okay, the first rationale is to avoid type mismatches. Okay, so let me just put that. So we haven't talked about this a lot, but in C++, there are actually many different types that we could use in the place of int that are just different kinds of ints. There's int, there's short, there's long, there's unsigned int, and you can, there's combinations of those, okay? So if we just make current size an int, that's not necessarily the type that the class is using to keep track of how big the container is. So for example, right here, in my vector class, there is a function named size. That size function may not, and actually probably is not, returning an int. It's probably returning one of those other integer formats. Okay, so if that happens, and I've declared current size to be an int, then I have a mismatch here. I've got an int on the left, and I've got some other kind of variable, some other type of variable on the right. So rationale number one for why to use size type is that then I don't have this mismatch. I can guarantee that the type of my variables that I have declared match the type that are being returned by the class. Okay. Rationale number two is that on any given system, it's not guaranteed that a variable of type int or of any other type is will be big enough to represent the number of items in the container. Okay, so for example, you could have a container that's so big that an int variable cannot be used to store the number of items in that container. So the size type that each STL class provides is guaranteed to be able to represent the number of items in any container of that STL class. Okay, so that was probably a bit of a convoluted sentence. I'm just going to put it out there. If you want to have that repeated, you can go take a look at the lesson. It's in the lesson. But for now, I'm just going to go with that. If it doesn't make total sense, that's okay. just know that when you are writing a program that uses an STL class, you should use size type when you want a variable that's going to store the size of the container. Okay. Any questions about size type? I've definitely been talking way too long without getting any sort of feedback from you guys at all, but I guess we'll just go with that if there are no questions. Okay, next thing that we need to talk about.
I have a question.
Yeah, go for it.
Can you go back for a second?
Yes, I can.
So for the size type thing, if you changed it from vector into vector, say float or double, would that also work?
Well, the reason that we're using int is because we actually have a vector of type int. To be honest, I'm not sure. It wouldn't really be the right thing to do, right? I mean, if you don't have any vectors of strings or whatever, then it kind of doesn't really make sense to use the size type from that vector. I'm not sure if it would actually work or not. Actually, we could just try that, right? First of all, I guess I never actually compiled and executed this file, which I should do. So let's do that. Okay, so that works fine. So I think what you're asking is, what if we just put string here, right? And we'd have to, in that case, downside include string. So first of all, let me just say, probably not a good idea, right? Why would you put a vector string here when that's not really what you're using? But in terms of just whether that would work or not, looks like that's going to be just fine, right? You're probably making the compiler do a lot more work when you do this, but apparently it works. Okay. Does that answer your question?
Yeah.
Okay. All right. Next, I want to talk about something called iterators. So in our example, we iterate over every element of this vector, right? That's the word iterate may or may not be something that you're familiar with, but it basically just means we're going to go and we're going to access every element in the vector one at a time. Other words for that is you could say we're going to traverse the vector. So with vectors, that turns out to be pretty simple, right? Because we can do it just like we would do an array. The problem is that most STL classes, that's not true. With most STL classes, you can't just access an individual element of the class by using square brackets or at or whatever, because the underlying structures behind the container classes are more complex. So the standard template library has provided a way for programmers to be able to iterate through any of the container classes. And in order to do that, basically, we've come up with an entirely new syntax for doing that. So I'm going to show you how to do that using the vector class. It may seem a little weird since it's not something we have to do with the vector class, right? We can just use indexing the way we do with arrays. But I'm going to show it to you using the vector class just so that you see it. And in the future, if you need to do this with some other STL class, you'll be able to, okay? So let's take a close look at this for loop here. And I want to say that there are basically 5 things going on with this for loop, okay? I'm going to say first we have a declaration. We're declaring the variable that we're going to use to traverse the vector. Then we've got initialize. Okay, so we're taking this variable of type size type and we are assigning it to 0 so that it will access the first item in the vector. Okay, then we are comparing, right? We're saying, is that number less than the size of the vector? Then we are advancing, right? We're saying, okay, whatever element of the vector I was accessing before, advance it down to the next item in the vector. And then here, this is how we access a particular element that is that I is used to access. So access. Okay, so basically, to use iterators, we're going to do exactly those same 5 steps, but we're going to use a slightly different syntax. And again, the point of this special syntax is that we can use the same syntax for any class in the standard template library, right? This syntax we have here using I and size type, this will only work for vectors. It won't work for any other class in the standard template library. All right, so here we go. Here's our declaration. Okay, instead of declaring something of type size type, which you could sort of roughly think of as being an integer, we're going to be declaring a variable of type iterator. Okay, so iterator is just a special type that is defined inside the vector class, and we can declare variables to be of type iterator. So that's step 1, declare. Initialize means we want that variable I to refer to the first item in the vector. The way we do that with vectors is we say print me.begin. Okay, so begin is a function inside the print me, inside the vector class. Print me is a vector, right? So begin is a function inside the print me class that returns an iterator that is pointing to the first item in the vector. So just sort of a side note here, I'm going to be using the term points to when I talk about iterators, but I just want to say that that doesn't mean it's a pointer, okay? I'm just using that term as a more general way of expressing the fact that, you know, the iterator is referring to that particular element. So I say that print me.begin. The begin function returns an iterator that is pointing at the first item in the vector. Okay, so hopefully you can see that this is just a new way of doing the same thing that we did here with the 0. Okay, number 3 is compare. Instead of saying I less than print me.size, we're going to say I not equal to print me.end. Okay, so I'm going to have to talk about this for a little bit because this is potentially confusing. First thing that I need to remind you of is that the reason this works in our for loop is that the index of the last element of an array is always 1 less than the size of the array. Okay, that sentence, you really need to understand that in order for this iterator stuff to make sense. Let me just go ahead and spell it out. In an array, the index of the last item in the array is always 1 less than the size of the array. Okay, so for example, if I have an array, I declare an array and I make it an array of size 10, the index of the last item in that array is 9, right? Because it's going to give me an array with indexes going from 0 through 9. Everyone clear on that sentence? Anybody want me to say it again or say more? I mean, basically, this is going back to week 4, right, of the semester. So that should make sense. So what that means is that when we use iterators, in order for this same for loop pattern to work, and we really like this for loop pattern, right? C++ programmers are used to using this for loop pattern. So we would like our iterator for loops to match the same sort of pattern. But in order to make that happen, the end function can't return an iterator to the last item in the vector. Instead, it's going to return an iterator to 1 item past the last item in the vector. Does that make sense? Because really, when I do size is the index of 1 element past the last element in the array. So this is just analogous. The end function doesn't return an iterator to the last item in the container. It returns an iterator to 1 past the last item in the container. Any questions about that? Anybody want me to repeat any of that?
So in a C string, if this was applied to a C string, it would return the null character?
Yes.
Cool.
Okay. Not sure if that helps you. That's great. Not sure I would if you're listening and you're not sure quite what that was all about, I don't think it's super important. And it may not be the best way to think about it, but if it helps you, that's great. Okay. Let's see. We've gone through the first 3 of these 5, right? We've done the compare. Now we need to do the advance. The way to advance an iterator, right? So the way to make an iterator go from 1 element to the next element in a container, the syntax is I++. Okay, just have to be super careful about that, right? Because it looks an awful lot like now I is an integer and you're just incrementing the integer. But that's not what is happening here. This is just an overloaded plus plus operator. It's overloaded to work with iterators, and it just it advances the iterator, right? It makes it point to the next element in the container. Anybody want to ask a question about that? Okay, and then number 5, the way we access the element from the vector using an iterator is we say star I. Okay, so this is kind of wild, right? It's very interesting that when we want to advance the iterator, we use syntax sort of as if I was an int. When we want to access what the iterator is pointing to, we use syntax sort of as if I was a pointer, right? The reason for that is that this is an iterator. It's a higher level thing than either an int or a pointer. And so the creator of C++ gets to choose what the syntax is going to be. And so they chose sort of whatever the simplest, most convenient syntax would be. And so in this case, it turns out that the simplest syntax is if you think of I as being an integer that's being incremented. And for accessing it, the simplest syntax is if you think of I as sort of being like a pointer that you're trying to dereference. Okay, but I guess the point here is I is not an integer, nor is it a pointer. It's this new thing called an iterator. And so the plus plus operator is simply how you advance the iterator, and the star operator is simply how you access or dereference the iterator. Okay. So this is pretty much all I want you to know about iterators. Iterators is goes very deep. There's a lot of stuff to learn about iterators. We're just going to kind of scratch the surface here. You're going to have to do something very similar to this in your assignment, but basically it's just going to be pretty much just copy and paste this forward, right? And let's just take another look at this and review what the functions are that you need to know about in terms of iterators, okay? You need to know how to declare an iterator. You need to know about the begin function, right? The begin function returns an iterator to the first element in the container. Thirdly, you need to know about the end function. The end function returns an iterator to the element one past the last element in the container. Fourthly, you need to know about the increment operator, which advances the iterator. And then fifth, you need to know about the star operator, which dereferences the iterator. It evaluates to whatever it is that the iterator is pointing at. Okay. Anyone want to ask a question about iterators? Okay, let me actually pull up a different file. The only difference here is just that I have, I have reverted completely to just using iterators to print the vector. Everything else I think is pretty much the same as it was before. Okay. So any questions about this code? I'll let you just stare at it for a minute. Okay. One more thing I need to tell you about iterators. Go ahead and look at this function header. We have done enough work this semester with passing objects as parameters that when you look at that, you should be thinking, wait a minute, something's missing here. Can anyone tell me what is missing from that function header?
The prototype doesn't match.
Good point. This is what I meant to ask. Okay. Now, can anyone tell me what is missing from that function header? And I guess you sort of have a big clue now what was missing, right?
The const.
Yeah, exactly. So, right, when we pass an object as a parameter, but that object is not being modified anywhere inside the function, we need to pass that object as a const. Okay, and so hopefully, I mean, it's probably okay at this point if you didn't notice that, but at least once I say that, that should make total sense, right? Passing an object as a parameter, it's not changing inside the function, so we're going to pass it as a const ampersand. Okay, here's the problem. Now that print me is a const, this statement right here is going to give me a syntax error. Because if print me is a const vector, then the printme.begin function is going to return a const iterator. In other words, it's going to return an iterator that cannot be used to change what it is pointing at. But I is just a regular iterator. It can be used to change what it is pointing at. And so C++ won't let me do this. If C++ were to let me do this, that would mean that inside this for loop, I could now use I to modify the vector, even though it was supposed to be const. Okay, so here's how we fix that in C++. Instead of using a regular iterator here to iterate through the vector, I'm going to have to use something called a const iterator. And that simply means that this is an iterator, just like it was before, but now I cannot use that iterator to modify the elements of the vector. Okay? Any questions about that? I think that's pretty much all there is to it. Oops. What I wanted to do is actually compile and execute this, just to show you that it actually does work. Vectors. Okay, that looks like it worked okay. And then I'm going to run it, and we just get the same output that we've been getting in the past. Just so you can see it. If I just used a regular iterator here, going to get some syntax errors, right? So the error is no viable conversion from, and you kind of look at all of this stuff and you think, I have no idea what that means, right? But basically, here's the difference, right? No viable conversion from const pointer to pointer. All right. So anyway, that's just to say that in this particular case, if print me is a const vector and I call the begin function on it, I'm going to have to use a const iterator in that position. Any other questions about that? Okay, so I actually have an appointment this afternoon, so I'm going to need to end a couple minutes early, and we're at a super good stopping point right here. So I have a couple more minutes if you have any questions about any of this. If not, then we're going to call it a day. Any questions about anything we've talked about so far? Let me just I'll just add one more thing. I'll just say that, again, we're just sort of scratching the surface with iterators. One of the things that you will learn about iterators, if you read about it in the textbook or online or something, is that there are a number of categories of iterators. The vector iterator is the most flexible one, right? With a vector iterator, you can use the increment operator and you can traverse the vector going forward. But I could also start at the end of the vector and use the decrement operator, I minus minus, and I could go backwards through the vector. Okay, so that's called a bidirectional iterator. Some of the STL classes, the iterators are not bidirectional. For some of the STL containers, if you declare an iterator, what you're going to get is an iterator that only goes one direction. You can only use the plus plus operator on it. If you try to go backwards through the container, so if you use I minus minus, you'll get a syntax error because the minus minus operator is not defined for those iterators. So an example of that is the forward list class that you may remember from the beginning of lecture that I showed you. That is a container where you can only use the plus plus operator on iterators. You can't use the minus minus operator on iterators. So none of that I just said is super important. The only thing I wanted you to get from that is just the idea that if you go deeper into iterators, you're going to find out that there are different categories of iterators that have different capabilities. You don't need to worry about that for our purposes. For our purposes, we're just going to use these 5 functions that we talked about today. The 5 functions being begin, end, not equal to, plus plus, and star, right? Those are the 5 functions that we used on iterators. 3 of those 5 functions I just mentioned are actually operator overloads, right? But they're still functions, so it's accurate to say that. Okay, any questions about any of that before we go? Okay, so we will continue this on Wednesday. On Wednesday, we will start talking about templates. And hopefully we will also talk a little bit about exceptions And that'll be it. Okay. So I will see you Wednesday.